I've got to tell you, this is going to be my favorite part of this entire series, route redistribution. It's a simple concept, moving routes between routing protocols, but it's my favorite because this is what the CCIE Routing and Switching Lab is built on. If you don't understand route redistribution, the CCIE dreams are not going to materialize because this is where it all happens. It's where a lot of problems get introduced. It's where your knowledge of the routing protocols and your knowledge of how to filter those routing protocols really comes into play. And man, it's a lot of fun. That's why I like route redistribution. It's a challenge. It's like a puzzle that you're putting together. So we'll start off with the foundations. Why on earth would an organization use multiple routing protocols? It's the first topic we'll talk about. Second thing is we'll look at what route redistribution is. Pretty much look at the definition. Finally, my favorite part is going to be the configuration of route redistribution. We're going to set up, at least in this video, with a straightforward redistribution example, moving routes from the RIP protocol over to OSPF. Let's start off with the question, why would you use multiple routing protocols within an organization? Well, I have my little political figure down there because most of the game with this is the politics. Here's kind of an example. I live out in Arizona, in the United States of America. Now, in Arizona, we're right on the border of Mexico. So we have a lot of people from Mexico that come up to Arizona to find work and things like that. And because of such a saturation of Arizona with people from Mexico, we speak two languages here. I don't, but most people do. They have all the forms, all the tax information, all the government regulations, signs, everything is in two languages, English in Spanish, because we have two major groups of people that are over here. Now, in the same sense, your organization is a giant political blob. The bigger it gets, the more politics gets involved. So the number one reason that I've seen in the world that people use multiple protocols is because of the politics of networking. Now, political boundaries, a lot of times people think of that as just, I don't like that group over there. We're going to create our own routing protocol and they're going to use theirs and we're not going to negotiate and all of that. And that may be true, but most of the time it's not a abusive relationship or something where people are mad at each other. The politics of networking usually goes into like regulatory considerations. I guess, let me give an example. EIGRP, the first routing protocol we talked about, is so simple and so feature-packed. People love it. But on the other hand, a lot of organizations have written political policies. When I say that, I don't mean like political as in government, but written policies for the organization that says we will not use proprietary stuff. Proprietary protocols, proprietary features, proprietary equipment. We won't use proprietary stuff as long as an industry standard that is acceptable exists. So because of that, a lot of organizations or divisions of those organizations won't use EIGRP because it is a political protocol. It's proprietary, I should say. So the politics keep EIGRP from being used. Now, maybe that's half the organization. Maybe that's the European, if I could say that, division of the organization that can't use EIGRP. Or maybe it's the United States side of it. But over in Europe, they say, well, you know what? We don't have that same regulation here. And that's a great routing protocol. It's very easy and our technicians understand it. So we're going to use it. And just like that, you now have half the organization that is using one routing protocol and half the organization that's using another. Now it's time for redistribution. You can see number two, why you use multiple routing protocols. You might be in the interim of a conversion. You're moving from maybe RIP to OSPF or OSPF to EIGRP, and it's a big network. So you do it in phases. This division will convert first, then that division, then that division. Well, in the meanwhile, you're going to need to redistribute so all the routing protocols have all the routes, even though you're running multiple routing protocols on the networks. Number three, vendor selection. Not only going into like Cisco versus Nortel versus Avaya, blah, blah, blah. We're getting into now vendor selection as in host-based routing. One of the things I've seen really jump up in recent years is Linux-based routers. There's actually an entire platform that was created on Linux that makes a Linux box look and feel like a Cisco router. Look and feel close enough that it feels like a Cisco router, but distance enough that they won't get sued. I mean, I can't tell a difference when I'm sitting on one of those. So you can actually set up a server that acts as a router. But of course, that device can't run EIGRP because that is proprietary. So maybe based on the vendor that you select, you have certain protocols that you can and cannot run. Finally, you have your application and business requirements. Mainframes, believe it or not, are making a comeback. People are realizing that, this whole idea of everybody having their own PC and their own desktop and all these applications sometimes just isn't productive for the business. And they're moving back to a mainframe style environment where people have essentially dumb terminals or terminal server style terminals where they're limited on the kinds of applications they can use. Now, that is also great for productivity because people don't have distractions and applications that they get sidetracked with, like web browsing. So with that in mind, some mainframes are locked into certain routing protocols, and the mainframe itself has to run a routing protocol. So based on that, you now have a business requirement or an application requirement that a certain protocol must be run. So let's look at the process. The process of redistribution is simple. And you're going to look at this and say, well, why is there so many problems? Here it is. Let's say you've got an organization that, for whatever reason, had to split into two. Half the organization ran RIP, the other half ran OSPF. Redistribution is this. We take the RIP routes and send them to OSPF. So OSPF has them. And OSPF routes, well, they get translated over to RIP routes. Ta-da! Redistribution done. Now, looking at that, you might say, why is it so complex? Well, let me add a couple factors here. First of all, what is the metric of RIP? Hop count, right? So however many hops between these routers, that determines the best path to the network. Well, what is the metric of OSPF? Well, now we're looking at cost, which is based on the bandwidth. So they're saying, well, this link is this much and this link is this much. Now, what happens when you send RIP routes that have hop count into a network that is based on essentially bandwidth to find the best way around the network? Well, you have now an incompatible metric. So how do you translate those routes? Meaning, when those come across, they have to have some kind of metric in OSPF. How do they get that? Well, you, as the administrator, type it in. Like, you get to say, for this route, it has this metric. This route has this metric. And that can be so tedious because you could have hundreds of routes that are coming over here from this RIP network. So what people will do is create something known as a default or a seed metric, which is just one metric. They say, you know what, for all the routes that are coming over here, all 100 routes, we're going to say that they have an OSPF cost of 1,700. Period. And they come into that domain with a cost of 1,700. So same thing going the other direction. We're sending, bandwidth or cost metric into a hop count world. You just type in how many hops those are going to be considered. So what that means is that your metric becomes unreliable. You just type it in and it's just a guesstimate that you're putting in there. So you don't really have an accurate way of saying this is the best path. Now, let's also zoom in on this. Look at our network topology. We have two paths between the RIP and OSPF networks, one here and one here. This is a breeding ground for routing loops. Here's the concept of a routing loop. We send RIP routes into OSPF, and because we want redundancy is good, right? We send OSPF routes into RIP, and we do the redistribution right here. Aha, a routing loop is born. The RIP routes will swarm the OSPF network, come right around and jump right back into RIP, then loop back around into OSPF, then loop back into RIP. You're going to end up with unreachable routes, routes that show up in your routing table as it'll say possibly down as the status because it doesn't know what's really going on with them. Packets can end up circling around the network endlessly until the time to live expires. It's bad news. So what you need to do when you have this sort of environment, you want to keep the redundancy, but maybe you send the routes from this direction into OSPF and you make the metric 100, a cost of 100. And maybe these routes are sent into OSPF with a cost of 200 because you want this to be your primary route and this to be your backup. Well, in that case, the routes will come in there with different costs. The routers will prefer one over the other. And that is one way that we can keep the routing loops from at least taking down the network. There's many ways to prevent routing loops. You can actually send some of the routes from RIP this way and some of the routes this way to try and somewhat load balance. What I mean is maybe you send 50 routes of those 100 this way with a cost of 100 and the other 50 have a cost of 200. Likewise, the mirrored routes, the ones that weren't sent over here with a cost of 100 get sent over here with a cost of 100. Are you following this? So essentially, we make some routes look more preferable this way and other routes look more preferable this way. And we're setting up a template of load balancing. I'm digressing a little bit because this is getting into manipulating route updates, but that's the complexity of route redistribution. And I haven't even touched filtering, where you have to filter certain routes that are going out. With that being said, this is a tiny redistribution example. What I did was I actually went to my CCIE title that I recorded for CBT Nuggets, and I pulled up the network diagram that we use as we go through the CCIE. This is actually the picture from the CCIE lab. This is a BGP topology, and I'm kind of scrolling around because it's huge. We actually take one piece of the network at a time as we're looking at all of those. You can see we've got all kinds of routers. We've got all sorts of, I'm trying to scroll around. It's just not working too well right here. I smooshed this down to a smaller resolution when we do this, but we've got all of these routers. Let me show you. That's just BGP. This is the network where we're running the internal routing protocols. Look at this. We've got, hang on, let me see if I can grab my window here. We've got the OSPF areas sitting around over here. We've got EIGRP sitting over here, looping around with OSPF and an ISDN network that's dial on demand, and we don't want that to come up as long as it's not necessary, but that needs to be able to redistribute routes from EIGRP should the primary frame relay connection go down. And let's explore down a little bit. Oops. Down here, I've got a little RIP action going on. I've got the backbone router that's doing redistribution from static routes over here. I mean, this is a big network, and well, I'm using big relatively. I mean, this is 8 routers. 8 routers that we're using for the CCIE lab environment. And that's just a small taste of what your network can look like with redistribution. Can you say routing loop when you're looking at this kind of thing? Because everywhere in this network is a potential for a routing loop. You can see redundancy all over the place. We've got backup paths, we got backup protocols. It looks, obviously this is a lab sort of environment because, real world, can you imagine that sort of network design? And yet it can happen. I say this to you because I don't want to give you the idea that route redistribution is just, it's a piece of cake. You just, I kind of did that when we first came to this slide here. You just send some RIP routes to OSPF, you send some OSPF routes to RIP, no problem. But when you get to a large network, that's where the problems begin. I'd like to wrap this nugget up by showing a live demonstration of redistribution in action. Now I'm going to start it off in this video as just a smaller network design. We've only got 4 routers. We'll add more as we get more complex. Router 1, 2, 3, and 4. Now, router 1, 3, and 4 I've already set up because that's a piece of cake. We've done that already. RIP configuration and just a small network. You can see router 1's got a bunch of 172.16 network environments. Router 3 and 4 are just OSPF area 0. It's just a single area, a backbone. And you can see that we've got the 10.52.x.x network that's sitting on router 4. Both of those, the 52 and the 172.16, have a 24-bit mask on them. So they're just Class C environments. What I want to focus on in this example is router 2. This is the first time we're going to see in this series a router that's set up with multiple routing protocols. And look how it's represented in that diagram. Router 2 is sitting between the areas. It's not really in RIP, but it is, and it's not really in OSPF, but it is. It's going to be running both routing protocols. Now at this time I have no configuration on there other than the base IP address configuration. It can ping router 1, it can ping router 3, no routing protocols exist. So I'm going to bring up TerraTerm. We're focusing on router 2. Do a quick show IP interface brief. I want you to see that serial 1.1 is connected over here to router 1. I named the sub-interfaces logically. So router 2 to router 1 is serial 1.1. And serial 1.3 is the one that connects router 2 to router 3, which is this action. Router 2 linking over here to router 3. So with that in mind, I want this interface to run RIP, and I want this interface to run OSPF. Let's make it happen. I'm going to go into router 2, go into router RIP. Now, the first thing I want to mention is that I am using version 2 down here. RIP version 1 is essentially history. Not many people use it anymore because it's feature-less. I'm going to type in version 2 to enable that and do a no auto summary to make it a classless routing protocol, which is one of the major features of RIP version 2. And now I'm going to turn it on for a network, and let's see what features this has first of all. See this version of the iOS doesn't let you use a wildcard mask. Some of the later iOS versions will let you use a wildcard mask with RIP, so I can focus it in on what interface I want to run. So we're posed with a little challenge. I only want RIP to run on this interface. I only want neighbors to form over here. I don't want neighbors to form over here. So unfortunately, with this iOS, I've got to, use the class full network 10.0.0, which makes it run on both. But I'm going to follow that up with a passive interface command for serial 1.3, which prevents RIP relationships from forming on this link right here. Now, be careful. Keep this in mind. We'll come back to it in just a little bit. RIP is not sending hellos on here because it's a passive interface. However, the passive interface command does not keep RIP from advertising this link into the RIP network. So RIP is advertising that network right there in the OSPF world to router 1. Now let's verify what's going on before we configure OSPF. I'm going to jump back and just do a show IP route on router 2. I can see that it's receiving all of the 172.16 networks that are over here on router 1, so that action is happening okay. So those are all being received by RIP. Now let's hop over to router 1. And I'm going to type in show IP route over here. And we can see that it's receiving one interface, and that is that link that I just mentioned. That's the link that, unfortunately, because of our iOS version, has to be advertised via RIP into this domain. Now, that's not going to cause a problem here, because we're going to be redistributing OSPF routes into RIP. It's just this one will kind of end up coming in twice. One as an external route for RIP, and one is one that just goes directly. Does that make sense? Let me just make sure I draw this out. Remember, we're going to be sending all OSPF routes into RIP. So this is being advertised directly by RIP. And it's being sent in via OSPF. So as we redistribute, let me put redist right here. As we redistribute OSPF into RIP, we're going to see that route twice. Thankfully, since this is a single link and we have no redundancy going on here, that won't cause any problems. No routing loops as of yet. So now we've got router 2 halfway configured. Show IP protocol, we're running RIP. Let's go in now and do a router OSPF 1. I'll do a router ID of 2.2.2.2 so we can have a good frame of reference of what our name is as the router. And I forgot what the interface was. There it is, serial 1.3. Let's do a network 10.1.23.1, which is the link over to router 3. I'll focus directly on that with a wildcard mask and say that is an area 0 link. I hit enter, and now we should have a relationship, beautiful, form with router 3, which was already configured. So we just went to a full neighbor relationship over here with router 3. Now, with that being said, let's do a show IP route one more time. Check out router 2. It's not having the routes I thought it would. Let me hit the up arrow and try it one more time. There it goes. Sorry, router 2 is a little slow on the gun. Took a sec for the SPF algorithm to run. So now we've got all the OSPF routes showing up here on router 2. So RIP, OSPF, both running on the same router. Yet, we are not doing redistribution. Router 2 is kind of the focal point of knowledge, if you will. It knows everything. But router 1 still doesn't know about those OSPF routes. I'll jump down here and prove it. Show IP route. All it knows about is RIP because redistribution is not happening. So all of these are going unmentioned to router 1. Let's make it happen. First thing I'm going to do, I'm going to start off with the simpler one. I'm going to redistribute OSPF into RIP. It's simpler because RIP doesn't have quite as many options as OSPF. The key thing to remember here is as you get into the configuration of redistribution, you want to make sure that you go into the routing protocol where you want the routes to go. Let me make that clear. Let me jump back to the diagram. I want to go into the configuration mode of the routing protocol where I want to do the redistribution. In this case, I want to send OSPF routes into RIP, so I'm going to go into the RIP routing protocol. So bring that up, router RIP. Here's the command to do it, and this is going to be the same command for every protocol. Redistribute, and then we get to choose what protocol we would like to send into RIP. In this case, OSPF. Redistribute OSPF, and we choose what process we're running, OSPF process 1. Now we come to the big question. Do you want to redistribute certain OSPF routes? What is the metric for these routes that you want to redistribute? Do you want to attach a route map? Holy cow, that's a big one. And that's something we're not going to cover in this video, but we will be covering as we get more into the advanced routing configuration. And then VRF is where you get into something we're not going to configure in here, VPN routing and forwarding instance. It's where you can have routes go into a VPN process, which that's beyond our world. So what I'm going to do is show you the options for each one of these. First one is I'm going to show you the options for match. I can say match and then what specific routes from OSPF I want to send in. If I say match internal, at that point it will only redistribute routes from router 2 that it sees as OSPF internal routes. So what does that mean? That means if router 4 is connected to some outside world here, we'll say we've got EIGRP that is redistributed into OSPF, well, those routes aren't going to end up in the RIP domain because they're considered external route. And you can see right here, I can choose internal or external. Now, if I leave the match option off, that means that it's going to send both of them. It will send internal or external, or I should say, and external routes into the domain, along with not so stubby area external. That's if this OSPF area was a not so stubby area that was being sent, the routes were being sent through. But as of right now, I'm going to leave the match option off because I want all of those routes to come in. The one that I want to make sure that I type in is a metric. Some routing protocols, if you don't type in a metric, then it's going to not send those routes. It'll set the metric to an unreachable metric, which in this case is 16. So I'll set the metric, again, this is just an arbitrary number that I'm going to make up. It's not reliable, but I'll type it in. I want to send the OSPF routes into this domain as a metric of 5. So all these routes will start off thinking they're 5 hops away to router 1. So you can see the metric has been set. Now the route map, again, I'm not going to show you the options. You can type in a route map name, but we'll get deep into that as we get further into this. I'm just going to hit the enter key. At that point, redistribution is done. Can you believe that? One command that we type in on router 2, and we're sending all OSPF routes over to router 1. Before we go the other direction, let's verify that. I'm going to hop over to router 1 and do a show IP route. Look at that. All of the routes are coming in here. You can see that they're all RIP routes, and notice this. Administrative distance is RIP. Hop count is a 5. So the metric that I set on all of those routes is automatically 5, and that will continue on. If router 1 had a link down here to, whoops, we'll say router 6 or something like that, that would end up having a hop count of 6. They will increment just like normal routes. It's not like the metric ends up being the same the whole way through the domain. So at that point, we have redistribution happening in one direction. Now, the other thing I want you to see right here is this link right there. Notice that that one did not get redistributed. Redistributed? You get what I mean. This one is using the original RIP route that I was mentioning right here. That's why I highlighted this. When we had RIP advertise this, it came in directly as a RIP route 1 hop away. Now, I speak loosely when I say it did not get redistributed because it did. Redistribution is happening, but why is it preferring the direct RIP route instead of the RIP route that's 5 hops away? Well, I have the answer highlighted for you right there because the direct RIP route is a better metric. So it's receiving both routes, the redistributed one and the direct one. It's just the direct one has a better hop count. So that one's going to end up being preferred. No real advantage one way or the other than just the fact that that's there. We're going to come back and visit that as we get into the more advanced videos because that can come back and haunt us with terms to routing loops. So with that being said, let's go the other direction. We've got RIP configured to redistribute OSPF. Let's configure OSPF to redistribute RIP. Remember, when we do this, we want to go into the routing protocol where we want the routes to go. That's probably the best way I can say that. So if I want the RIP routes to go into OSPF, I need to go under OSPF. Figuring out that direction is half the game. So let me jump back over to router 2 here. And I'm under RIP right now, so I'm going to type in router OSPF 1. So now I'm under the OSPF process. Same command, different protocol. Redistribute, this time RIP. And now look at our options. The first thing that I want to make sure I mention with OSPF is this one. If you forget the subnets, OSPF does automatic summarization. It will take all of these routes back to a class full standard. So those routes would come into OSPF as 172.16.00/16. Now, if that is your intended result, if you want it to summarize during redistribution, then by all means, leave that keyword off. In this case, it might be a good idea since there's only a single path to get there anyway, as long as you're not using any other 172.16 networks in your organization elsewhere. So for now, I'm going to send the subnet so we don't do the automatic summarization. Now let's look at our other options. Metric. We have to set the metric. We have to type it in just like we did with RIP. But this time, instead of typing in a hop count, I'm going to be typing in the cost or what metric I want OSPF to see as it comes in there. Now I'm going to just choose a metric of, we'll do 1800. 1800. So all the routes will come from RIP, all these 172.16 networks will reach router 2, move into OSPF with the default metric of 1800. Now we have a big decision to make, the metric type. Think back to our OSPF videos when we talked about our two options. We have external type 1 and external type 2. Do you remember the difference? External type 1 is the metric that will continue to increment, meaning it starts at 1800 as it comes into this domain, and then it will add the cost of this link. So maybe 1864 if that's a T1 line. Then it will add the cost of this link. So maybe it's up to 18 or 19 something, if that's a cost of 64. So the point is it keeps incrementing the metric as you go throughout the domain. That's a lot of times a good option, but sometimes, if you only have a single path to go there, you might choose the default, which if you don't type in metric type, it will choose a metric type of 2, which means it will come in as 1800 as your metric, and it will stay 1800 as it goes throughout this entire domain. That might save you a few processor cycles because it doesn't have to keep adding those costs. And since there's only a single path to get there anyway, I mean, what's the point of really adding up all those metrics? You got to go that way, so we might as well just say it's 1800 all the way across. So that's what we'll do in this case. We'll choose a metric type of 2. So we've set the metric type. Route map, I mentioned we're going to talk about later. Subnets keeps it from auto-summarizing as it goes into OSPF. The only one that we haven't talked about is the tag. Oh my word. For those of you going on to the CCIE, this tag feature is your best friend. I will explain what it is right now, but not use it. What the tag is, I'll type in tag and hit question mark, is just a number, a 32-bit number that I can essentially mark these routes with. That's what it should have been called, a marker. Because as these routes move from RIP to OSPF, we can mark them, or I guess you could say color them with the tag. Uh, Have you remember the switch world? I know we're talking all about routing, but remember that good old protocol of 802.1q or ISL, our trunking protocols, where it would literally color the packets with what VLAN they belong to? Well, this is the same kind of thing. We can color these RIP routes as they come in. Maybe this is the RIP route of 172.16.1.0/24. We can go ahead and color this with the color 52. That's a tag. That's what this value is right here. Now you might wonder, well, why would you do that? Because later on, when we get to route filtering, you can actually match things based on the tag. For example, maybe router 4 ended up with a wild WAN link connection over here to router 1 as a backup link. And you don't want these routes coming from RIP into OSPF and looping back around over here to router 1. So what we could do is set up a filter. And we could say on router 4, hey, router 4, if you have any, routes that have a tag of 52 or are quote unquote colored with 52, don't send them this direction. Sorry, put a wall there. So we can tag things as they come into the OSPF domain, which is just a marker that we as administrator can refer to later on. The tags don't influence anything else. They don't influence the metric, nothing like that. It's just a little marker. Again, I'm not going to show that to you now, but boy, is that thing handy for being able to tag your routes and marking them for filtering purposes. Let's see. Is there anything else I was going to tell you here? I don't think so. That's done it. We've redistributed RIP into OSPF. And I was just typing something to remind me. We've been setting the metric for routes as we've been going all along. But rather than setting the metric every time you do a redistribution, some administrators prefer to set a default metric. Now, this is an option that's not only here for OSPF, it's also available for every other routing protocol. I can say default metric 1800, and then whenever I do redistribution of any protocol, RIP, EIGRP, anything, I don't have to type in a metric after it anymore. All routes that are redistributed into OSPF will have this default metric unless you choose to overrule it by typing in a metric on your redistribution command. So I'm showing it to you under OSPF, but I just want to prove it. Under RIP, I can also type in that default metric and choose a specific metric that I want to set when I'm sending routes into RIP as well. Okay, so we have that option. I think that's all I wanted to show you. So now let me hop over to router. Holy cow, look at this diagram. This is horrible. If you were to walk in and look at that diagram, you would just be completely confused. Let me clear this off. Whew, better. So I'll add our arrows. We're redistributing this way and this way. Much better. So I'm going to come over to router 3. Do some verification. Show IP route. And at this point, that's my success yodel. We have OSPF external type 2 routes that are being sent in. Notice the cost of 1800 that are being received on router 3. And just for grins, let's walk on over to router 4, do a show IP route, and we can see those same external type 2 routes. Look at that. The metric stays the same because those routes are, external type 2. External type 1 would continue to increment. So at this point, we have done redistribution between OSPF and RIP, both directions. Both domains now have all the routes they need. Now that's the basics of redistribution. That's just moving routes between one protocol to another. As we get further in the advanced routing, we'll start looking at some of the other features and utilities, tools that we can use to help filter those routes out so they don't cause any devastation in a large routing environment. So to wrap things up, let's look at the high points of what we talked about. Number one, we looked at why we would use multiple routing protocols. We looked at some of the political reasons, some of the business-specific reasons, some of the vendor incompatibilities between different platforms, proprietary protocols, so on. We looked at what redistribution is all about, moving routes from one protocol to another. And finally, of course, the bulk of this video has been focused on the configuration of route redistribution. And in this case, we focused between RIP and OSPF. I hope this has been informative for you, and I'd like to thank you for viewing.